Now, so we have a shunt DC motor. The ratings are 230 volts and 10 horsepower. And I'm going to expect you to know what those ratings mean without having to tell you. The armature resistance, 0.4 ohms. A field circuit resistance of 200 ohms. We're given full load armature current 37 amps. So now I've asked you to sketch and label the equivalent circuit and complete the calculations for lock rotor current in the armature, copper losses in each winding, mechanical power developed, PMI, mechanical losses and total losses, and motor efficiency. And so again, we talked about a 4-step process. The idea is that you should sketch your equivalent circuit, get the numbers from the problem on there, think about what you've been asked for, and then analyze the circuit and complete the calculations to come up with the answers. So, the 230 volts, 10 horsepower. Remember that when a power rating is given, even if it's given in watts or kilowatts, it's still the mechanical output of the motor at full load. So, we can assume we're told the motor is running at full load, draws 37 amps, and the output power delivered to the load, 10 horsepower. Okay? The 230 volts is a rating. Remember, that pertains to the source. And so don't confuse that with E0, because some of you will. On the diagram, it's very important to get ES and E0 in the right spot, as well as the rest of the numbers. Okay, so now I've got a second page set up here, and it's the equivalent circuit. And so when I click on it, the circuit will come up. So now I'm going to take that circuit, and I'm going to copy it. I'm going to pop it in on that question page here. Okay, so now I'm going to resize. And put it back in screencast view. Okay, so there. Now, note then that here, right, the source voltage is 230 volts. In parallel with that, we have the shunt circuit. Includes the rheostat, but that's not important. RF at 200 ohms and IF, the current in that branch, is important. The armature circuit between terminals X and Y, we have RA at the 0.4 ohms given, the current in the armature at full load 37 amps, and the output power at that time 10 horsepower, and we have E0 labeled here. Okay, so let's think about our calculations. Remember that we are worried about the current that flows in the armature circuit during the startup condition. We're ignoring the field circuit, even though we know there's a current there too. It's the armature current that we're interested in. During startup, E0 is not built up yet because it depends upon the armature moving, but it's stopped. So that means the 230 volts is dropped across the 0.4 ohms of armature resistance. And so to do the calculation, part A, I'll get a bit faster at this as we go along, right? ILR is equal to the difference between ES and E0. If E0 is 0, the numerator just got ES up there. And we're going to divide by RA. Okay. Equals. So I'm sorry if that is a bit sloppy, but like I said, I'm going to get better at this as we go. So in the numerator, we got 230 volts. In the denominator, we have the armature resistance labeled on our circuit, 0.4 ohms. And so that calculation gives us a lock rotor current of 575 amps. Oh, think about what that means. Our rated current is here at 37 amps. If we compare the 575 to that, I think that's like 20 times rated value. Oh, it's 15.5 times rated value. Okay, so that's a lot. Now, based on that calculation, the idea is that we said that as soon as that big inrush starts, the motor starts to move immediately, E0 builds up, the voltage drop across RA drops. Hopefully the current will never reach that value. The idea then is that 5 to 6 times the 37 amps is what we expect, and we have to ensure that the motor and the power supply can withstand that surge. We'll talk about what to do about it later if that's not the case. Okay? Now, so part B, let's think about the copper losses in each winding. So we said that the copper losses have to be calculated, and they are I squared R. So in this one, we got two windings, right? We have a shunt winding, and remember that the R loss will include the shunt circuit, really, right? Because there's a rheostat in there, and that got some of the 200 ohms. And we have an armature winding, which we have represented as the 0.4 ohms with the 37 amps flowing through it. So we got the two numbers that we need for the armature. For the field, we got to calculate the field current before we can come up with it. Now, you know, if you want to think about circuit analysis, V squared divided by R is the loss in the shunt circuit. And so you got the voltage drop across there. You don't need to calculate that current, but we're probably going to need it later. So we may as well do that. Okay? So in the armature winding, which I'm just going to call arm, we have that loss is IA squared multiplied by RA. And so that gives us 37 amps squared multiplied by the 0.4 ohms. And so that gives us a value, right? Square root of 37 multiplied by 0.4, and that gives us 547.6, and the unit for that is watts. Okay, now right here then I'll say shunt. Now for the shunt winding, we have to calculate the shunt current. So IF, and you can, you know, this is about circuit analysis, right? Or we got the equations wrote down back where we started the equivalent circuits, and so you can refer to them if you need to. IF is equal to ES divided by RF. And so we have for this one, if I can squeeze it in there, 230 volts divided by the resistance of the winding, which is 200 ohms. So that means that IF has a value for this question of 1.15 amps. And that somewhat depends on the position of the rheostat, right? And so remember, we said that for any given question, we won't change the value of RF at all. So we'll assume that, that value of RF is constant for the question. And so IF is 1.15, and that should be amps. Now, I should be able to erase that ohm sum that I got there, and go back and put an A in there, because that's amps, right? Okay, so now the shunt loss is IF squared times RF, and so we have our 1.15 amps, and I always include the units. It's good to get used to that, and multiply that by the 200 ohms. And so remember, like we said, now we could have used 230 squared divided by 200, right? 200 ohms. And so if we do that calculation, 1.15 squared times 200, and that becomes 264.5. Now remember, I said the copper losses in each winding. I never asked for the total. And so when I ask for them in each winding, I want them separately, right? And so I'll expect you to do the individual calculations like that. And so we got the armature loss there, and yes, watts. And so I didn't put that in. I never really had enough room, but yeah, it should be watts there, right? And show the shunt loss then as 264.5 watts. Now, not that I had to find a total on that. I had to add them up. Simply will do, right? Okay, now let's go for part C. And so I know this is getting a bit messy. Let's do part C up here. And we try to keep as much of that on the screen with the circuit shown as we can. Later we're probably going to have to scroll down a bit, but in any event, for part C now, remember that PMI, and we got an equation for that, right? So, there's a certain amount of memorization here, I guess. But remember, you get most of this stuff with some understanding. I think PMI is the power developed by the armature, and so there's our armature. And so the power of any component is the current that goes into it times the voltage drop across it. And so, E0 times IA, right? And so if you forget, you should be able to remember it like that, right? And so E0, and I probably won't give you any formulas for the quiz, right? So normally I don't. I expect you to remember them as part of learning this stuff. And so here we don't know E0, right? And so we got to calculate it. Okay, so remember, we got an equation for E0. E0 comes from analysis of this loop. It is the source voltage, subtract the voltage drop across this resistor, which we can calculate because we got the two values. And so we start off then by saying, for this one, that E0 is equal to E source subtract IA times RA, which is the voltage drop across that armature resistor. And so that means we have 230 volts subtract the voltage drop across the armature resistor is 37 amps for armature current, multiplied by the 0.4 ohms. And so that voltage drop becomes, give me a sec now, 230 So that voltage drop, 37 times 0.4, is 14.8 volts. Now try to keep three significant figures in your calculations, right? So 14.8. And that means, I suppose, that, if you don't round it, you end up with 4 significant digits there, and that's okay. You can round it if you want to, call it 15. And I went with 215.2. Now, if you rounded that to 215, that'd be okay. But, 215.2 volts. So now, PMI then is equal to, and just let me pull out a different color here now, and oh, I didn't mean to do that. So we got E0 times IA, so 215.2 volts multiplied by 37 amps for IA, and PMI then has a value of 7,962.4, and the unit is watts. Now, let's think about how else could we have found that value? Anybody got any suggestions on that? Okay, so think about our equivalent circuit. And in our equivalent circuit, we got a power that's delivered to the circuit by the source. And we haven't calculated it, but we will in a minute. And that is P in. Okay. Now, so this example is taking a lot longer than I was hoping. In any event, now we got a power that comes out of our circuit here, and that is PMI. And the difference between P in and PMI is what? The losses that we account for in this circuit, which are the copper losses, and we calculate them. 1 hair, 1 hair. So the reality of it is that PMI here is equal to P in subtract our copper losses, IA squared. If I can make that an A. Okay, so my wrist's getting tired. Times RA subtract IF squared times RF. Alright, and we got the values. Now, P in we haven't calculated, but we got the values for the copper losses. Now we can calculate P in relatively easily. And so think about, again, the fact that, there's more than one way to do the calculations here. And really the reason why there's more than one way to do the calculations here is that the DC model gives us this equation here to calculate the power developed by the motor. And, for AC machines, we won't have that, right? And so that makes the analysis of this a bit easier. It means there's always more than one way to do stuff here. And so for the DC machine, we could find PMI by doing this. Got most of the calculations done. Okay? Now, I'm going to have to scroll down a bit. And so remember that mechanical loss and total losses is next, and then the motor efficiency. Okay, so if I pulls that down here, we have part D, and P out now, remember, was 10 horsepower. And I will expect you, of course, to be able to convert that to watts. And so 10 horsepower multiplied by 746 watts per horsepower. And that gives us 7,460 watts. Okay, so now across the shaft of our machine is where the mechanical or constant losses occur. And so that constant loss, if I can write that as CL, and that is the mechanical loss, right? And remember, PMI is bigger than P out. The difference between the two, the shaft loss. So we have then PMI subtract P out, and that gives us 7,962.4. And like I said, if you did some rounding there, you know, keep 3 significant digits is preferred. Subtract 7,460 watts. And so that constant loss, now our mechanical loss, becomes equal to the difference, of course, between those two numbers. And that is approximately 500 watts, right? And so I think it's 502. 7962.4 subtract 7460, and we got 502.4 watts. Okay, now then the total loss is the sum of all the losses, right? And so the copper loss plus the constant loss. And so we have 547.6 264. I didn't realize that this was going to be painful after an hour. And the 502.4 watts, and the sum of all those $1,314.5, and of course the unit is watts. Now, and so the last thing for us to do is calculate efficiency. And so for efficiency, think about the fact that we have the power out. We don't have the power in, but we got the total losses. And so, you know, we can approach this calculation now in a couple of ways, right? We can say P out over P out plus total loss, and we can calculate P in. We've got two different ways to calculate P in. right? Because P in is P out plus the total loss, which is the sum now of this number here and this number here. Okay, so what I'm going to do is I'm going to say that I line for efficiency, yeah, for parity, and so so now I line is equal to IA plus IF, right? And so again, that comes from circuit analysis, or if you remember the equations. And so we got 37 amps, and IF was 1.15 amps. And so 38.15 amps. Now, so if I says that power in is equal to E source times I line, and I think I'm going to run out of room again, then we have $230 volts multiplied by 38.15 amps that we just calculated, and that gives us power in at 8,774.5 watts. And I'm not sure how much different the value would be if you added the 7460 and the 1314.5, but with me here keeping 5 significant digits and stuff, I assume it would be exactly right. So now if we got power in, our efficiency calculation should be straightforward, right? And so eta is equal to P out over P in. We'll give the efficiency as a decimal. Standard to express it in percent, so multiply by 100, and that converts to percent. So if I can scroll down another bit, make room for that, right? Then we have our P out 7460, and we divide that by the 8,774.5 watts and multiply by 100. We come up with an efficiency for that motor under this condition of well, we might as well call it 85%, 85.02%. So now, our thing now is, remember that we need to sketch the circuit, get our values from the question onto the circuit in the proper spot, and then this comes down to circuit analysis, and that circuit relay, right, is a source with 1, 2, 3 resistors, or 3 loads, because I don't like calling the armature a resistor. So 3 loads. And so, relatively easily, but the approach and what we're asking for and the way we does it is a bit different from the way you've seen it in Electrotech 1100. The reality of it is not that much more difficult. And so some practice with this stuff. The new terminology is where you need to focus for the start, because you need to know what everything means, all the new terms and stuff like that. And then some practice with numbers, right? And your approach, you're always given, normally you're likely to be given the ratings. You'll probably be given RA and RF and another piece of information. In this one, it was armature current. It won't always be armature current. Could have gave you E0, right? They're pretty common. What about if I started you off with efficiency? Well, you'll see one like that. When you start off with efficiency, you got to start off with this formula here, right? And so the problems are very often different. Now, so anybody got any questions about that? This here, that's a Greek letter eta. It's supposed to look like a lowercase n with a little tail on it, a written in. Eta as a Greek letter. I think that's a lowercase eta. There's uppercase one too, right? Eta, ETA. And that just represents efficiency. Okay, so I'll